Welcome students for this my last video for this semester. In this video we will look at how nuclear reactors actually work. We'll look at the energies associated with these nuclear reactors, and then we'll look at some more aspects including nuclear waste and fusion within stars. So let's go ahead and get started. So the idea here, nuclear reactors are just glorified tea kettles. They're really, really fancy, but the idea here is that we allow uranium to be bombarded by neutrons. A specific isotope of uranium can be bombarded by neutrons, and it will fragment. It will cleave to form two new elements and several neutrons. This cleavage process creates multiple neutrons that can further cleave and further react, and it keeps generating, and you can keep this going as what's called a chain reaction. Now, part of it is getting things just right. This seems very simple, but you have to get things just right, because if you allow not every neutron that hits a uranium atom is going to be absorbed. They have to be moving at just the right speed. If they're moving too fast, they'll be bouncing off without being captured. If they're moving probably too slow, they might not have enough energy to stick. And so we have certain ways of controlling this bombardment, of slowing them down or speeding it up, so that we can keep this going at a steady pace. We need a certain amount of neutrons to be absorbed to keep this going at a constant rate. So we need essentially a critical mass of uranium. We need below that and a subcritical mass. Any neutrons absorbed, the process will basically be slowing down. It's always going to be decelerating. If you produce two neutrons, but only say 30% of those two neutrons get absorbed, that every 1 out of 3 times a neutron collides, it absorbs, it's going to slow down, because that means the first 60% of the neutrons will be absorbed, and then 60% of that and 60% of that eventually is going to be down to 0. A rounding error. That it'll slow down. So we need a certain amount so that enough of those neutrons absorb, they keep it going at a constant rate. Now, uranium-235, it's kind of a problem, because uranium-235 is only less than 1% abundance of all of the naturally occurring uranium. So to get that and purify that and keep it at a high enough ratio that we can keep these reactions occurring is hard to do. However, through a completely different process, we can bombard the more common uranium-238 with neutrons to form plutonium. Now, we can't do this directly in the standard reactor because this process takes some time. That the first bombardment takes 2.3 minute half-life to convert our uranium into neptunium, so it's not long, but then it takes another beta decay, which with a half-life of 2.3 days to start converting this into plutonium. But that plutonium can then be used in other nuclear reactions. But looking at this schematic of the nuclear reactor, a pressurized water type, that basically we have reactor rods, and we have various control rods that we can stick in and out of here that will help. Essentially, some of them will help to slow down the neutrons, some of them will be there to absorb the neutrons, but it's there to regulate the neutron absorption so that we can keep the pace steady. You have coolant. The coolant is the water kettle part. We're essentially absorbing all the heat of this reaction occurring, using it to boil some water down the road, and that water turns to steam. That steam turns the the giant water wheel, and that's what generates the energy. Just a very, very effective way of boiling water. Now it needs some thermal shielding to make sure it doesn't melt its way out of the container. It needs some biological shielding to make sure it doesn't irradiate all the scientists and all the engineers that are making sure it's working. It needs the coolant to remove the a lot of the heat and keep things at a steady pace. Sometimes helps slow down the neutrons. But there's a lot of engineering to make sure this is as safe as we can make it. But the first nuclear reactor was created by Enrico Fermi. The idea that we was able to show a controllable reaction, not just chain reaction, but a controllable reaction that he could make it work and make it produce a steady stream. That it's not just one radioactive decay, but a continuing radioactive decay. So he set up his first reactor in the squash court beneath the stadium at the University of Chicago, done in December 2nd, 1942. Now, at the time, it's like they weren't quite sure this was going to work. They weren't kind of sure what was going to happen. They had they had an idea, but they hoped it was going to be controllable. They had a bunch of uranium and graphite bricks, and the graphite's there trying to slow down the neutron cap. This basically to stop it going, and so they basically slowly pulled out the blocks in there and let it. As they pulled out the blocks, they were able to measure the radioactivity being produced at a controllable rate. Now, they had some safety measures. They had like a dead man switch where a guy with a hatchet ready to cut a rope to hopefully swing in the protective thing to shut it back down if it starts getting out of control. They were hoping they could get a constant rate and not keep building. So, and they also had students with buckets of this like neutron absorbing material that they're going to hopefully pour onto it. Hopefully, if things went poorly, maybe Chicago's gone. If things went poorly, but not quite as poorly, if the scientists were able to use their fail-safes, maybe just they're dead. But Chicago's fine, and that was what they were hoping for with their fail-safes. But this was an example of the first atomic pile, where it was literally piled up into a little thing, and very interesting setup, but is showing that, we can harness this to make nuclear reactors. We can harness this, we can control this if we get the engineering down. And so the parts of the reactor, if we break it down, we have the reactor fuel. It's typically just metallic uranium, but it could be a ceramic uranium oxide or uranium carbide produced as plates or pellets or pins, but it's essentially assembled in various geometric patterns. We often seal it up and clad it with stainless steel or zirconium alloys to help keep its shape as it decays and converts into other stuff. Because remember, it's going to decay into different compounds as it goes. And so you can see it changing the shape in the figure. So you see the densification that takes place after a short period of radiation on the bottom photograph compared to the original compound on the top. So if they don't kind of seal that up, some of that can break apart. If it breaks apart in the reactor, then you have to kind of stop and reset, and that's a little bit of a problem. Typically, you need a moderator. You need something that slows down the neutrons to help them be captured. So water and heavy water is a moderator. Graphite is a really good moderator, as is beryllium and certain organic compounds. In fact, when we were making the atom bomb back in World War II versus the Nazis, we figured out very quickly that graphite was a very good moderator. They did some bad chemistry and threw out graphite as an easy option, and so they were stuck. They found heavy water being a good moderator, and so they were fighting to get control of the only major source of heavy water, which is deuterated water in Europe. And so it was a constant fight between us within spycraft to try to slow down their heavy water production and try to keep them from having that. But they never really got it off the ground because heavy water was not nearly as good for making bombs as the graphite was for controlling the neutron absorption. Now you need some sort of control system, something to slow it down, to let it peter off. And you need powerful neutron absorbers like boron or cadmium. Something that will absorb the neutrons and not really fragment and not absorb it better than the uranium will. And of course, then you need some way to remove the heat energy. This produces a lot of heat energy, and we can remove this by air, helium, carbon dioxide, water, various organics, liquid sodium, or even liquid lithium. But this heat energy will then be used to boil the water that runs the turbine. So we're just transferring the heat energy away, and then you need some sort of radiation shielding, the steel lining that will prevent the thermal damage, and you need the high density concrete to protect from the radiation to the living peoples. So now there's various different types of reactors. It depends on what you're doing. There's some simple ones where you can just like boil the water directly and the steam then turns the turbine. You can do like a multi-loop one where the liquid coolant heats up a separate steam which then turns the turbine, or you can have multi-loops of transferring heat to boil the water. So this one, like the bottom left one, liquid metal cooled reactor. So you have liquid sodium in the primary loop and the secondary loop, and then the idea is like we can achieve maybe higher temperatures at a nominal pressure. That sodium is also a very efficient heat transfer medium, so that it does introduce some further complications, but we can get maybe better heat transfer. And so the other one's like well-developed technology, but the coolant has to be pressurized to prevent bulk boiling in the core. So we have to keep this high pressure so we don't accidentally boil out our coolant here, and that'd be bad. This one, yeah. But this one has to have a much bigger core in order to make this work, because we're allowing the coolant to boil in the core itself. So it needs to be much bigger than these guys. So it all depends. And most of these, you see these little loops. This is the cooling solution. So we need to cool the water and allow it to condense back down so we can heat it back up again. And so this is where we get the condenser. This is where you get those big weird cooling towers you always see and associate with the nuclear reactors. That they need to not spend a lot of energy cooling down the water. And so it's basically, it sends this water to the just essentially top of a water slide and allows it like to air cool as it swings down this water slide, so that it heats up the air a lot, but we don't have to spend a lot of energy to cool this back off again. And so we can allow a lot of the cooling to be done by the natural environment. Now, of course, there's two very large problems with nuclear reactors. When things go back, actually, there's several. I mean, there's obviously low amounts of fuel source. It's sometimes hard to get, but when things go bad, they go really bad. When danger is minimal in 99% of the cases, that unlike you blow up a oil plant, you have raging wildfires, you have environmental waste you can clean up, but you can start the cleanup process once the fire goes out. When a nuclear reactor explodes, we produce a lot of nuclear waste everywhere, and the whole area is irradiated and maybe unlivable for many, many years. We can think of like 3 Mile Island, we can think of Chernobyl, we can think of Fukushima in recent memory, really. It's like where some of these houses are still irradiated and not really safe to go live in anymore because of the problems. But the other major thing is the nuclear waste is very long-lived. And you remember, first-order decay has a constant half-life. This cannot be changed. Spent fuel rods, in order to be considered safe, should undergo 10 half-lives to be considered minimum safe risk for health. And so, if it takes just say carbon-14, if it takes 5,000 years, we'll just say round down to 5,000 years, to take one half-life, 10 half-lives would be 50,000 years. We have to store this for 50,000 years for it to go down to what's considered safe. However, nowadays there's certain ways to reprocess these fuels and use some of these fuels, the byproducts of these reactors, into a different type of reactors that can hopefully remove or use up some of these longer-lived products. So if we can allow these guys to further react through more nuclear bombardment, we can maybe convert them into something a little bit more something that decays a little bit faster, and we can get further energy. It's like if we were able to capture some of the energy from the waste product of our car and use that for more fuel, it's like, oh, it's not nearly as bad. We get more efficiency out of it. Now, so sometimes you can separate these guys out. Like strontium-90 is one byproduct of it. It only needs to be stored for 288 years. If we got plutonium out of it, this needs to be stored for 240,000 years. So if we can then use that plutonium up in a different reactor or separate it out and dispose of it faster, the 10 half-lives of strontium would only be 2,880 years instead of 2,400,000 years. So if we can find other uses for these radioactive products, it's maybe not as bad, but still some of this is bad. A lot of governments have difficulty thinking in the long term. They can't even balance budgets in the year you got. Now think about keeping things going for thousands of years. It's a little bit difficult. It's a challenging engineering process. Now, of course, when everyone thinks of nuclear chemistry, they think of nuclear bombs. What makes a nuclear bomb different from a nuclear reactor? And the basic idea here is a nuclear reactor is set so that it can remove the heat that's produced, and it is set to react and produce energy at a constant rate. For every 2 neutrons it generates, it absorbs one of those 2 neutrons to generate 2 more neutrons and keep going. Well, for every 2 neutrons you absorb, you produced 4 neutrons, and every 4 neutrons you absorb, you produce 8 neutrons, and so on, and it has a cascading effect. That's when you have a nuclear bomb in the making. To do that, they create what's called a supercritical mass of uranium. that essentially generates a runaway reaction, one where the majority of the neutrons will be absorbed and producing more neutrons, and this will create a domino effect that produces a lot of energy very rapidly that will continue to build up. So, in order to do this, a lot of nuclear bombs essentially store two subcritical masses and that need to be rammed together. That the standard atom bomb, the little boy, essentially has a ring, like a donut shaped reactor, and like the plug. That when this hits the ground, it fires the ring, or it fires the plug into the ring, and then from there, it essentially initiates the neutron, and it starts the reaction. There's the other one, I think, the Fat Man, which is a plutonium-shaped one, that essentially is a hollow sphere. A hollow sphere that it's subcritical as a hollow sphere, but when it goes off, essentially through very carefully engineered explosions, causes the hollow sphere to collapse into one supercritical ball, and that causes that to go off. And essentially, once it goes off, it starts to build and build and build. Heat goes up and up and up and up and up. And pressure, of course, because the gases are building and the heat is producing faster and faster and faster. The gases don't have enough time to expand. They're not expanding fast enough, and they're not able to essentially dissipate the heat fast enough so that we eventually goes boom, and the gases expand all at once as that mushroom cloud, taking everything with it. Creating both a shock wave and like an EM pulse and radiation all over the place. Massive heat wave of pressure of gases spreading out everywhere. Well, the last thing before we talk about some of the energy is fusion. So we might talk about the energy, we might not, but fusion is the process by which stars form every element that ever exists. That all elements are essentially formed from the fusion of hydrogen and helium in the sun, or in stars like the sun. That most stars start with the basic helium atoms, and this combusts and converts hydrogen fuse together to form a positron and a deuterium atom. So one of the protons gets converted into a neutron and it kicks off a positron part. The deuterium plus another hydrogen gets converted into helium-3. So it's a little lighter version of helium. And then once we build up enough of the 3 heliums that they can convert into a single normal helium and regenerate 2 new hydrogen atoms. Or if a hydrogen atom bumps into a helium-3, we can generate another positron and a regular helium. So all this process is just going on that produces helium and slowly converting all the hydrogens in the sun into helium. Each of these processes are producing massive amounts of energy. It produces something like, I guess I'd be 90 billion joules of energy alone. That first reaction, per mole of hydrogen, this produces something like 89 billion joules of energy. Now, it requires incredibly high temperatures and incredibly high pressures. So temperatures of over that's 40 million Kelvin, and high pressures to push them together and make sure they don't escape. But of course, remember the pressure, the gravity of the sun is incredibly dense. It's 274 meters per second squared, the gravity on the surface of the sun. And it only goes higher as we approach the center of the sun. So it's already at very high pressure, but it's not that every ball of hydrogen will react. It's just you need really high pressures and very high temperatures to achieve this. But the sun's going to keep working and keep converting hydrogen to helium. Once all the hydrogen is, of course, used up, then the helium can start to react. That the helium starts to then absorb and convert into new elements like beryllium. And then helium can bind to beryllium to form carbon, and carbon can bind to helium to form oxygen. These reactions have various speeds, various energies, and there's other ways to form the other elements, the odd number elements. But essentially we see a series of fusion-style reactions that eventually produces all of the elements in certain ratios till we get to iron 56. Now, iron 56 is the most energy dense atom we can generate. From there, there's a series of slow or rapid neutron captures that can occur that form the heavier elements from there. But a lot of the heavy stuff are generated only once the sun goes supernova. Once the sun goes supernova, it can fling out all these heavy elements, and these are going to become essentially what the universe is made of. But so you may be wondering, well, the first law of thermodynamics says energy is neither created nor destroyed. So if matter is conserved, as we're just converting over here, how do these guys generate energy? How do they generate energy? We're not breaking any bonds, so how do they generate energy? And that's where we get to our dear friend E equals mc squared. C is just a constant. So M is mass. So we're converting mass into energy. And the idea here is that nuclear reactions occur. There is a tiny fractional mass that is lost as energy. This fractional mass is often seen as the strong nuclear reaction. That essentially the radioactive element, the mass of the radioactive element is not equal to the sum of the masses of the decay products. I mean, in the short run, yes, if you round everything, they are equal. But in the long run, if you take things out to their umpteenth decimal place, you can see there is a small mass defect between these. Now, we need to use the isotopic mass to make this work. We have to use the exact mass in AMU, not the isotopic mixture. You can't just go, oh, chlorine 35.45. You have to use, is it chlorine 35 or is it chlorine 37? And you have to use the exact mass in order to get these numbers right. Because when we're going to nuclear reaction, only one atom, one isotope is actually reacting, not all of them. But so, for example, in the nuclear reaction where uranium-238 decays to 234, an alpha particle, if we look at the mass, uranium-238 is actually 238.0003. That thorium is not 234, but 233.9942. And alpha particle is not 4, but 4.0015. So if we add those guys together, the thorium plus the alpha particle, the total mass is 237.9957, not 238.0003. So if we take the mass of all the products and subtract the mass of all the reactants, we find out the mass defect is only 4.6 milligrams per mole of reaction. 4.6 milligrams per mole of reaction. But that is still a working thing. Now, in order to get joules, a quick math thing says a joule is equal to a kilogram meters squared per second squared. The meters squared per second squared comes from the speed of light squared. So if I convert the 0046 grams to kilograms, I get that, this reaction produces 4.1 times 10 to the 11th joules per mole of uranium decaying. This decay process still produces this much energy. Now, please note, you have to be given the exact masses. You cannot just use the number on a standard periodic table. You have to be given these, or you have to look them up. Otherwise, it won't work. But so, what is the reaction of the uranium nuclear reaction? One neutron, U-235, goes to tellurium-137 and zirconium-97 and 2 neutrons. The neutron is 1.00866 and uranium is 235.043923.062. Tellurium and zirconium 36.92532 and 96.910950716. Okay, I had to write these down before I flip it over. So, my reactant. I can go ahead and one neutron cancels out with one of those neutrons. So I'm going to say the total number of products is going to be this, this, and this. So let's do that. 96.910950716 plus 1.00866 plus 136.92532. So the products are 234.844930.7, and I'm going to subtract out 235.043923062. Minus out that 235.043923062. Subtract out that. So what is our mass defect? Did I do that right? 632. Yeah, 33. So the mass defect is 1.9. Actually, it's like, my bad. 0.19899236. We can probably round at this point. Let's see. The lowest number was 1, 2, 3, 4, 5. But 1, 2, 3, 4, 5. So we're going to round there. 0.19899 sig figs. So 0.19899. So we have to divide that by 1,000 to turn this into kilojoules. But then we got to multiply by the speed of light squared. So the light is 2.998 times 10 to the 8th. We got to square that. When we square that, how much energy? This produces 1.788. 1, 2, 3, 4, 5. 2, 3, 4, 885 times 10 to the 13th joules of energy per mole. Per mole. So that is what, like 17 trillion, almost 18 trillion joules of energy per mole. That's a bit much. Bit much. So you can see why these guys are so dangerous. Produces a lot of energy. Lot of energy. So the last thing I'll talk about, and that's where I'll leave you, is that, as I said, the iron heart is the death of a star. That idea that iron is the magical tipping point where most of the reactions stop, because the mass defect is due to the strong nuclear force that is stabilizing the nucleus. The energy of the energy that binds this together. That as we move from left to right, the nuclear binding energy is going up. So elements below this are going to fuse together till they get to elements that are a higher nuclear binding energy. Well, elements above iron will start to drop back down in terms of nuclear binding energy. And so these guys are going to be weaker and want to break apart. These guys are going to be more easy to fission into different elements. That iron essentially is the low point, the valley of energy density, where once this happens, no element really wants to easily form. Now, it's not saying they cannot form, because obviously we have elements that are higher than iron, 56. But iron, it has one of its highest abundances because that is one of the particular stable points within atoms. Now, if you want to learn more about this, well, you're going to have to take some deep dives in Wikipedia and read some textbooks. But the idea here is that iron has a magical stability that it's hard to beat, and that's why iron is so dang abundant. But that is where I leave you for this semester. I thank you for your attention. Hopefully these videos have been useful to you. Have a good rest of the year.